For generations, the physical laboratory served as the practical foundation of physics education. It is where abstract theories meet the friction of the real world. But today, that foundation is showing its age. In schools worldwide, educators face a chronic reality of underfunded departments, broken or missing equipment, and severely limited access time for students. When an entire class must share a single aging apparatus, the physical hardware becomes a bottleneck. It restricts instructional pace, limits the ability to repeat experiments, and often turns active investigation into a passive demonstration. The answer to this crisis is not pouring more money into fragile hardware. Instead, we can separate the rigorous process of experimentation from physical limitations. By moving past the hard constraints of the physical workbench, we can scale experimental learning to every student simultaneously. Hello, colleagues. I am Gani Zarumukamaz, and I would like to present a structural solution to these hardware limitations. This solution is the Integrated Digital Pedagogical Model, or IDPM. It is a framework designed to replace high-cost equipment with accessible digital infrastructure. At the center of this model is PhysHub. It is a digital ecosystem where abstract physics concepts are rendered tangible through interactive, screen-based environments. The engine driving this access is a bring-your-own-device approach. This turns the smartphone in a student's pocket into a primary scientific tool. PhysHub and personal devices do not substitute the scientific method. Instead, they remove the mechanical barriers that often prevent students from engaging with it. When administrators hear digital ecosystem, the immediate concern is the budget required to maintain servers and IT support. We engineered a low-cost, high-reliability technical stack. Front-end delivery is handled through Google Sites, creating a stable, universally accessible interface. We pair this with Cloudflare for simulation hosting. This ensures zero downtime and rapid execution without placing a heavy load on local networks. This cloud-based approach avoids the maintenance cycles that make physical lab benches so expensive. Because infrastructure is remote, experimentation isn't confined to a single classroom. Students can run complex physics simulations on the bus, at home, or in the hallway. This architectural simplicity allows pedagogical methods to scale across different schools without the risk of hardware failure. To see how this works in practice, let's look at the actual PhysHub interface in action. Scanning a QR code opens the static equilibrium module, presenting digital suspended weights. Adjusting mass parameters using the sliders immediately changes the system's variables. Visual feedback is instantaneous. The system recalculates, shifting the red force vectors to show the new equilibrium. These are not pre-rendered animations. The simulations are driven by mathematical engines that calculate results based on physical laws. In a physical lab, testing a new variable requires untying strings and swapping weights, a process that can take minutes for every single data point. By removing that mechanical friction, the student can spend more time analyzing the data and less time managing the equipment. When students work remotely, teachers often worry about academic integrity, specifically students simply copying data from one another. PhysHub addresses this with a dynamic generation engine built into each experiment. Every session begins by assigning unique starting parameters. 3 students working on the same assignment face the exact same physical problem, but with different numerical variables. This makes simple copying impossible. Each student must apply the physics formulas to their own unique set of numbers. This ensures that student results are a direct reflection of their own calculations, rather than a neighbor's work. Beyond the software, we also focus on the student's experience during the experiment. In traditional settings, the fear of damaging expensive equipment often creates a high-anxiety environment that can distract from the lesson. A virtual environment acts as a safe sandbox. It allows students to test extreme variables and push parameters to their limits without any risk of hardware damage. We supplement this safety with gamification elements, like interactive quizzes and immediate feedback. This treats errors as a natural part of the experimental process. By removing the risk of equipment failure and the mental tax of manual setup, students can focus more on asking what-if questions. This model has been rigorously tested through pedagogical research to measure its real-world impact. The findings are clear. Students using the IDPM framework showed a 20 to 30% increase in academic performance compared to those using traditional methods alone. Furthermore, survey data showed a 40% increase in student motivation toward the subject. These results correlate directly with the features we've demonstrated: the ease of access, the anti-cheat mechanics, and the safe space for experimentation. The data shows that when we remove the physical friction of the lab, students demonstrate a measurable increase in both performance and interest. For educational technologists and administrators, the evidence suggests a clear path forward. PhysHub is built on an accessible architecture that does not require proprietary hardware or institutional grants to implement. Start using student-owned devices as legitimate lab tools and integrate these simulations into your curriculum today. We can move past the limitations of the PhysHub workbench by utilizing the hardware students already carry. Physics education is becoming more accessible because the most versatile laboratory a student needs is already in their pocket.